maybe we'll get started. It's 4 o'clock. We'll let people trickle in as they come. So extremely happy and delighted to introduce Professor Karthik Duraisamy, who's come from aerospace. He's a popular figure.
I'm also in your department.
Aerospace and the mechanical engineering department. He's also the director of MICD, which is Michigan Institute for Computational Discovery and Engineering. He's a popular figure for a lot of the research that he does, and also by virtue of leading MICD, as I mentioned before. His research interests are in various aspects of computational science and artificial intelligence, much of what we will hear about today in this seminar. In terms of other information, he is the director of the Multi-University Air Force Center of Excellence on Reduced Order Modeling, and the principal investigator of the University of Michigan Los Alamos Center on Advanced Computational Sciences. He's also the founder and the chief scientist of the Silicon Valley-based startup Geminis AI, which is focused on developing digital twins for various processes, industrial processes, and energy applications. It is our pleasure to have you here. Looking forward to hearing your talk.
It's mine as well. And I've not given a talk. I guess I've given one talk in Michigan in my 11 years here, departmental seminars. So
this is special.
Yeah, yes. This is very special. Thank you for having me. All right. So I'm not going to be talking about AI today, although I might mention it here and there. But in some sense, these methods also fall in that class. So I'm going to be talking about predictive reduced order modeling for complex multi-scale multi-threaded systems. So I want to start with, why do we need this, and what do I actually mean by reduced order models? So here is some of the typical examples that we deal with in at least in our Air Force Center. So this is a single element rocket combustor. So you have fuel being injected here, you have your oxidizer injected here, and there is combustion. So you see there are very large pressure oscillations. So if you look at the magnitudes of what I'm showing here, you get a sense of how strong the pressure oscillations are. This is not like gas turbine combustors where perturbations are like 0.2%. Here, perturbations are 100% and very high pressure, right? So complex physics, flow turbulence combustion. So running one calculation like this for 50 milliseconds of real time is about a month on a university scale cluster, right? So that's the kind of expense it takes. That's how expensive these simulations are. But the problem is in a real rocket combustor, you have hundreds of these elements. And in a real rocket engine, you have 8 such engines, right? So this is basically pretty much an impossible problem to solve, even on some of the most powerful computational facilities in the world. And all of this is just to run one calculation at one condition, right? So it quickly becomes intractable. And there are many other problems that fall in this class. If you think of nuclear fusion, you're thinking of global climate simulations, global weather predictions. So many of these simulations fall in this class of being prohibitively expensive to get the accuracy that we need. So we want to reduce the cost or reduce the complexity of the simulations. So how can you do that, right? So there are 2 routes you can take. Reduce order modeling and reduce fidelity modeling. I think somebody's Zoom windows open or something with the volume on. All right. So you can reduce complexity by doing a mathematical order reduction, which is having these complex equations, but to solve them on lower dimensional manifold, which is the approach that we're going to take. The other approach is what I call as reduced fidelity, where you can take your governing equations, simplify certain terms, or maybe you can say I can ignore radiation, I can make an axisymmetric approximation. So those are physics-inspired reductions, okay? So today we're going to be looking at mathematical reductions, which is we still want to keep the same set of equations, but we want to mathematically reduce complexity by finding lower dimensional manifolds on which the equations are hopefully less complex. Okay, so that's the idea of reduced order modeling, and at least everything gets talked about as reduced order modeling, but what I mean in the context of this talk is this particular mathematical reduction. Okay, that's the idea. So what do we want to be doing with these models? So as I mentioned earlier, if I have a rocket combustor, first I want to predict the future state. I have some initial conditions, and I want to predict the future state very efficiently, right? Or there is some parameter in the problem that is changing. Maybe the temperature in the oxidizer manifold is changing, or some other boundary conditions are changing. How does that impact the solution? And the third thing is, I just told you that I cannot do a full simulation of the full system. Okay? So can I build reduced order models for components of the system and then stitch them together to be able to perform a prediction on the full system, right? So these are some of the goals. And many times, especially when it comes to data-driven modeling, it is kind of important to distinguish between what is truly prediction and what is reconstruction, right? Reconstruction is you've seen some dynamics offline and you're just trying to recreate the same thing, or you're trying to interpolate in parameter space. So all of those have value in many contexts, but in the present context, we want to develop methods that can reliably give you future state predictions, parametric predictions, and also integrated system predictions. Okay, so that is the goal of what we're trying to do. And there are many ways of doing this. You can use machine learning methods based on, say, some neural operators, or you can use regressors. The classical reduced order models, there are ways in which we can take simpler physics models and then inject some learning components in the middle and try to make predictions. And then we have adaptive reduced order models, which we're going to talk about here. So adaptive reduced order models tend to work with very less data, as I'll show you. And potentially, they can be very accurate in very complex physical and parametric regimes. But of course, there is a catch, and the catch is you're not going to get many orders of magnitude speed up over your full order model. You may be going to get 1 or 2 orders of magnitude at best. So that's the high level picture of what we're going to do here. And let me jump into the talk. I want to acknowledge Cheng, who is now faculty at Kansas, and Chris and Nick are research scientists at Sandia and Florence Livermore, respectively. And much of this work was done as part of a larger team. And you can go look up the center website to see what else is happening. All right, so how many of you have seen projection-based reduced order models before? So just about 1/4 or 1/5 of the audience, which is fine. So I have a few starter slides to get you oriented with what we're going to be doing, okay? So let's start with the full order model. Think about this as your high fidelity CFD simulation of this full system, where you've done the spatial discretization, and so you're left with a set of ordinary differential equations. This F would be all of your spatial fluxes and source terms in your CFD solver. And typically, for the example that I showed in the first slide, you have about 1 billion unknowns. Okay, so that's your full order model. So the goal is to develop this reduced order model where you find an alternate set of equations that is much lower dimension. You go from 10 to the 9 to 10 to the 3. And so the relationship, and you go from Q to QR. Q is in n-dimensional space, QR is in k-dimensional space. And to go from Q to QR, you can either use a linear basis or a linear manifold on which you're approximating, or it can be nonlinear. In this case, in this particular slide, I'm showing you this reduced basis approximation where effectively you have this basis matrix V, right? So each column represents a basis vector, and you have QR, which is so each row of QR represents the coefficient of that particular basis mode to give you your full order state, right? This is no different from a basis representation like finite elements, at least in representation wise, but in reality, your finite elements give you a local basis that is completely unaware of the underlying solution. But here you're able to get away with this because this basis V knows something about the problem, and that is why you're able to make the reduction, right? In your finite element field, you have an ad hoc basis that's not tailored to the solution, whereas here we find V that knows something about the solution, and that is what makes this possible. Okay, so that's the linear approximation, and the simplest way you can construct a linear subspace is by, let's say I have a flow around a gas turbine combustor. I can take the entire flow field and I can put that as a linear vector, right? So I have a billion unknowns. I can put that in a matrix as a column of a matrix. Then for other flow conditions or in other times, I can get these other snapshots. So I have my snapshot matrix A, and I can do a very simple singular value decomposition. And the columns and every matrix has a singular value decomposition. And the first few columns of the left singular vector can give me the best basis under, and it is the optimal basis under a few conditions in the Frobenius and L2 norm. Okay, but that's not the only way you can do it. You can also construct nonlinear dimension reduction methods where instead of just the linear decomposition, you can have an encoder where you have your high dimensional vector, you encode that to this low dimensional place, and then you can decode that to come back. Okay, so these are two different methods. So how does this help reduce order models? So again, I just told you, you have this high dimensional state, and you can construct this latent space where you have your reduced state, and then you can take the reduced state and then project the Gaussian equations. Okay, so that's what is called an intrusive reduced order model, and I'll show you more details on this. There are also non-intrusive reduced order models where the first step until here is exactly the same. You find some kind of low dimensional representation, and then instead of using the Gaussian equations, you just use data to learn this model. Okay, so that's a non-intrusive reduced order model. So we've done a lot of work in this space as well, but what we have found is they're very good in recreating things they've seen before, and unless you find some kind of magic basis, they're not generalizable. Okay, so we're going to be following the intrusive problem approach, and the idea is very simple. I'm just go through the next two slides and then I'll pause to see if everyone is on board. Okay. So again, same process. So this is your full order model in n dimensions. You find a lower dimensional linear manifold V. It could be done, for instance, using the singular value decomposition. And then you find this approximation where you're approximating Q using a linear combination of those basis functions. And then you're going to take VQR, and you're going to go back to this equation here and substitute VQR wherever you have Q. And then you hit this entire equation with a V transpose. And if your basis is orthogonal, V transpose V's identity. Okay, so you get this set of equations. This is your Galerkin reduced order model. So you've gone from n dimensions to k dimensions. And so instead of solving for n unknowns, you're solving for k unknowns. Okay, so is this clear? Do you see how we achieve dimension reduction? Is there anything that you would like me to explain?
So this is just a linear transform?
Yeah.
And so there's reduction in the degrees of freedom, but then how does that represent a reduction in the original, say, partial differential equation or anything like that? So you still have F, which is the same operator, right?
Yeah.
You have Q tilde, which is a reduced order transformation.
Yeah.
So I'm still not seeing, like, if you're looking at flow through arteries, right, or
Yeah.
something like that, like, how are you accounting for scales and changing your differential equations?
Correct. That's the next part.
Okay, good.
You caught it. So I think his point is, yes, I only have K equations, but I still have this F, and evaluating F is order N, right? So I've not really reduced the complexity, I've just reduced the number of unknowns, but the complexity is more or less the same, right? But this is the first step. This is the Galerkin-reduced Sodom model. If this were a linear problem, if F was some AQ, then we can do a lot of pre-compute and this problem won't be there, right? So the way we address this cost is, again, the problem is this entire F is here, so we've not reduced complexity. So what we can do then is take samples of F, okay? So forget all of this part. I'm going to introduce this operator P, and this operator P kind of looks like this, okay? If your N was 5 and your K was 2, if this was my P matrix, it basically says, grab me the fourth component of F and the second component of F, okay? And you can use linear interpolation to reconstruct this F. So the way to read this is, PF are just samples of F. You have this whole domain, you're just picking a few points where you're evaluating F, and then you're able to reconstruct the whole F. I still have not answered your question because there is still the whole thing.
I can be patient.
Yes. Patient for 30 seconds, okay? So now if I substitute this back in this equation, I get this equation, okay? So PF is you're evaluating F at only a few samples, and then I have this operator. So this still doesn't answer Eric's question.
Carl,
Sorry, it's been 10 years since we last spoke. Call. But the thing is, this entire matrix can be computed before we initialize the reduced Sodom model. So this whole thing can be pre-computed, and this is a K by S matrix. So when the ROM is being run, you are multiplying a K by S matrix and evaluating the reduced Sodom model at just a few samples. That's like a preliminary way of reducing complexity. But if you argue with me that still does not solve the closure problem, it's still a lot of information that's missing, that's coming in the second part of the talk. Okay, but this is the idea now. So you do some offline work and you compute this matrix. So you have a K by S matrix, and then you just evaluate F at a few locations, at S location, instead of evaluating F at all N locations, which was the reason for your full cost. Okay, so this, yeah.
Sorry, just to confirm my understanding. So far the reduction in dimension is only in spatial, not in time.
Correct, not in time. Although space and time are related in the sense that this system would be much less stiff than the original system, so you can actually get away with a larger time step in principle. But you're always losing something. But this is, again, note that we are still in the introduction slide, right? So we have a lot more to do to tackle the kind of problems that I spoke about initially. But this is the general idea. These elements are going to come back and forth. So anyway, this is how we are evaluating S samples, and then we are multiplying that by a K by S matrix to evolve the state, and that's how we get a reduced complexity. Okay. Yeah.
How do you do the pre-compute of that? Is there, will the final solution be subject to how you calculate that, or?
Yes, it's not. So this is the simplest ROM you can get, simplest cheap ROM that you can get.
Okay.
And so this V is from snapshots of the flow field, and U will be from snapshots of F.
Okay.
So you compute those, and this is what gets you off the ground, okay? But there are many challenges, and now this is, in reality, you're going to have some kind of discrete time stepping scheme. And in reality, you would have some kind of a scaling. But this is how the actual ROM will look like. But it turns out that not only is this not as accurate when we're doing future state predictions because you're missing some information, it may also not be stable, right? Because as you know, in finite elements, if you apply Galerkin projection, it works well in elliptic problems, but if you go to hyperbolic and parabolic problems, you have issues. It's the same issue with these Galerkin reduced order models. So instead, you can do, there are many ways of getting ROMs that are more stable for more general problems. And one of the ways you can do this is by using least squares projections. Okay, so you're going to have your reduced order decomposition, and then you would do an L2 norm minimization. And just like least squares finite elements can get you stability for non-elliptic problems, least squares reduced order models can also get you that. So that's the idea. And again, so that's like, this was, least squares finite elements is many decades old, and least squares reduced order models are at least 2 decades old. And there are many, many other developments that have happened in reduced order models. But what we want to do in this talk is to explore the question whether these reduced order models can be truly predictive in the kind of problem that I showed you earlier, and address these very complex things, very complex physics under the conditions that I mentioned earlier. And again, reminding you that these calculations, even for one injector, is expensive, and real rockets have many injectors. Okay.
Karthik, can I ask you a question?
Yeah.
Can you go back to the encoder decoder slide? And I want to ask you if
This one?
Yeah, this one.
Yeah.
So if I had if I had an autoencoder, right, that gets me QR.
Yeah.
And then I evolve that autoencoder, evolve that QR, right, in time, right, as a neural ODE.
Yeah.
Right. Then does that essentially, well, it's not quite this, because
This is the evolution of using the neural ODE.
well, but that's that N is time dynamics.
It's your neural ODE.
So N is time dynamics.
Yeah.
Okay, but it's not N of QR comma theta equal to 0, right? It is DQR DT.
Sure. Yeah.
Yeah.
And can have a dq r by dt term in it.
Okay. True. But then essentially, is that not? Would that dynamics learn the same thing as what you would have in your Galerkin reduced or intrusive reduced order model?
What we have found, we spent a lot of time linear, quadratic, neural, and everything in this data-driven fashion. But
because if you think about what you're doing, right?
Yeah.
I mean, your key operator, right, is some way to sort of sample that F.
Yeah.
Right?
Yeah.
So effectively what you're doing is some function sampling of that F.
Correct.
Right? So which means that I should create a learnable function. In fact, what actually I was going to ask is P a learnable function, right?
Yeah, P is where you pick the samples.
Yeah, P is essentially like a picking operator, right? It turns on at different points.
Yeah, and there are many ways of finding the right P, and that's not the bottleneck. You actually are hitting on something, right? So when I started the project 6 or 7 years ago, and somebody said, "Oh, an intrusive ROM was Karen Wilcox." A non-intrusive ROM, like you said, and they didn't even go neural, they just went linear and quadratic. They could get almost 99% of what the intrusive ROM was getting. Okay. But the thing is, neither the intrusive ROM nor the non-intrusive ROM were any good when approached in situations where new things were happening, like there are chaotic flows or
So they're just fits.
they're both fits, in fact. You know, we like to think that, oh, this data-driven model is the one that is a fit, okay? But even when you're projecting the equations, you still have the governing equations at hand, but the basis is not adequate. So when the projection error that's going out was actually killing us. Okay, so you're right.
But all of them are information loss, right? They all have information loss by definition.
Correct.
Right? No matter whether it's intrusive or non-intrusive, right?
But
So the question is, right, is whether, it depends on what you call interpolation and extrapolation.
Yeah.
Right? But I think the question is really whether it's throwing away more information than, and you're saying that probably it's throwing away more information.
Actually, no, I'm agreeing with you. I'm agreeing with you that if done right, and if you had a lot more data, right? So the non-intrusive approach requires more data because it does not have the operator at hand. If you have enough data, the intrusive and the non-intrusive ROM, as I showed you, can give very similar results. I did not believe this until I actually saw that. But I'm going to tell you that the culprit is the basis. If the basis is bad, then whatever you do, whatever learning you do, and whatever projection you do is not going to save you. So just to give up the climax of my talk, the way we address that is by updating the basis with the solution. I'll get to that. But yeah, with enough data, a non-intrusive ROM can pretty much do the same as an intrusive ROM.
Got it. And remind me in this autoencoder world, right? The basis is that compression operator, right? That FIOQ is sort of playing the role of the basis, basically.
Yeah, that's the base.
That's the basis.
Effectively.
So in an autoencoder that should be learned, right? So that the basis should be reasonable, I would assume, right? Or not?
They're actually not even as good as the POD basis for various technical reasons. But I agree with you that if you have enough data, then the intrusive and the non-intrusive ROMs would give you the same result, okay? But there's a lot more to it. So anyway, so give me 1 second to to show you what equations are underneath, right? So this is a nonlinear multiscale multiphase problem. As I said, there is flow, there's turbulence, there's combustion, there's acoustics. And these are the equations we solve. They seem simple, but Navier-Stokes equations are complex by themselves. This is compressible, there are additional species. And the worst thing is these very, very stiff source terms. And these are heat release rates, and you can see the magnitude is intense. And no snapshot is the same as the previous snapshot because of chaos. And that means things go out of basis, out of manifold all the time. So this talk has 3 parts, and given we have a lively conversation, I'm just going to focus on 2 parts. Okay, so first part is, yes, we can write these ROMs, but can you keep them stable? Okay, so that itself, it took us about 3 years to solve. I'm not going to go much into the detail because that's more numerical method, right? But I'm going to focus on these 2 parts, right? So how do you get back the information that you threw away, or information that might go away otherwise? Again, let me quickly run through the first part, just for completeness. You can read more in this paper, all 50 pages of it. So the idea is similar to what I mentioned earlier, but there are some additional scalings and additional variable transformations that get you a better reduced order model. Okay, that is guaranteed to be stable, at least in a global sense. And with those kinds of models, we were able to get about 4 orders of magnitude speed up in our calculations. But not too different from what I showed you, but with a little more transformation. So this is, a demonstration example where, for instance, single element combustor, it takes 15 CPU hours to run the full auto model. The reduced auto model can run in about 10 seconds. So that's almost 4 orders of magnitude. Of course, there is some information loss, but to engineering accuracy, it's not bad, okay? But there is a problem. The problem is that basis becomes inaccurate, whether you're doing autoencoders or whatever you're doing. So here is an example. So here I'm not even running a reduced order model. I'm taking the gas turbine combustor, building a reduced basis based on this much data, okay? So that many snapshots of data was used to construct basis. And I just look at the projection error, that is about 0.5% error, which is tolerable. And as soon as I go to future state, I get a lot of error. Now I say, okay, maybe I've not captured enough detail, so then I increase my window to this much. But as soon as I go into future state, I again get a huge jump. And you can use more data, but that does not solve the problem. So the point here is, whether you're using linear basis or using autoencoders or whatever it is, they're all really good at recreating what they've seen before. But because this is a chaotic flow and every flow snapshot is unique or distinct from the previous one, as soon as you go to prediction, you're basically, the error is shooting up, okay? So, so what can we do? But anyway, the first 2 years, even in this part, the ROM would not stay stable. And we developed some methods to do that. And again, we explored nonlinear manifolds too, like not just linear. All right, so let's now get to how do we address this loss of accuracy? Okay, so I'm going to switch from static basis to adaptive basis. I'll tell you what it is. And this is the core of the talk, right? This is what gives you that predictive capability. So, so this is the idea, okay? So let's say your high dimensional problem is in 3 dimensions, okay? This is the trajectory of your true high dimensional physics, 3D. And let's say I find the best 1D projection of this 3D dynamics. And this is the best I can do, right? No matter what, no matter whether well, I guess you could have a nonlinear manifold that kind of follows that, but it will still be in 3D, right? So this is the best 1D approximation to this 3D problem, right? So this is n equal to 3 and k equal to 1. So obviously, you're going to lose a lot of accuracy. But let's say I have an adaptive 1D basis where these lines are screwed up, but when the solution at time t1, this is my projection, right? This is my space on which I'm projecting the equations. Then at time t2, this is how I'm projecting this is the manifold on which I'm projecting the dynamics. And at t5, this is the manifold on which I'm projecting the dynamics, okay? So then I'm actually following the solution manifold, and I can get a 1D solution to match. Okay, so that's the general idea. We are getting rid of projection error, or at least minimizing projection error by changing the basis as we move in time. And here is where the intrusive ROM wins out, because the only way we can adapt the manifold, or at least the most sensible way we can adapt the manifold, is by having the Gaussian equations at hand and using those to guide the adaptation. Okay. So going from a static basis to a dynamic or adaptive basis that follows the solution allows you to reduce dimensionality and still maintain accuracy. So your projection error is minimized.
So are you pushing back and pulling forward between your higher dimensional solutions, or how are you doing that slope detection of manifold detection?
Correct. Yeah, let me show you that. Yeah. So again, going back to the previous thing, right? Your static basis, if dq by dt equal to r of q, there should be a qr here. RFQ is the reduced order model, your static basis, this is your time basis, and that's your test basis, that is how it will look like, whereas the adaptive basis ROM, this is going to become a function of time, just like I showed you earlier. Okay. So the high level idea, so there's a lot of fine grained detail, but I'll tell you the high level idea. The high level idea is at every time step, you have the full order model operator, okay? So I want to nudge, I wish I had this additional slide, but anyways, that whiteboard. Anyway, so what we do is the following. At every time step, let's call it t+1, we have the basis at the old time step, and we're going to be adding a delta to it, okay? We're going to be nudging that delta. And the way we're going to nudge that delta is to find the delta in such a way that the residual of the full order model operator is minimized at a few sampling points. If I reduce the residual everywhere, then I'm computing the residual everywhere, and I go back to that order n. The simple thing is, I have my full order model operator, so I will plug in the reduced order model solution into that, and only at a few points will I sample that, and then I would nudge it. But there are again some catches there, but that's the high level idea. And again, I'm sparing you some of the math. Again, there's another 55-page paper that you can read, but I'll condense it. So again, you have a basis at some time step V, and you're going to update that basis with some addition delta. And typically, the update to that basis looks like this. I'll show you the exact expression. So this is the full algorithm, okay? So again, it's still, I mean, there's a lot of things going on, but effectively, it boils down to what I was telling you, okay? This is actually how the reduced order model looks like, given a basis. It is just that least square solution explicitly written out. And then we will do a state estimate at some sample points. And then we would update the basis. We'll update the basis at a few sampling points using this expression that basically minimizes the estimated solution, the difference between the estimated and the full solution. And then we also have to update the sampling points every few time steps. And that is done by minimizing this equation. Again, there are different ways of approaching this. Again, the details are in the paper, but the high level idea is you are sampling the solution at a few points and using that to guide the nudging of your basis, okay? There's also some other things, complexity things, but again, in the context of this talk, I just want to hit the high note and guide you to.
Is it the same as evolving the basis also in time?
Actually, that's a very good question. So one of our collaborators, he has written an equation to evolve the basis. So dV or d delta by dt.
Yeah.
Right. So that also an approach, yes. Yes. But the adaptation is the key thing. And we've done some computational complexity studies, etc. Okay. So now here is how it works. So in this case, it's this rocket combustor. And this is the data that we use for training to construct the initial basis set. And then in the rest of the region, we are predicting. Okay, so this is effectively your training region, and this is your prediction region. And these red points or red regions is where you are evaluating the full order solution operator. And that's how you are getting the cost reduction. In this particular case, the sample points cover like 0.5% of the domain. And you can get a good amount of prediction. So here, I showed you a 10,000 speed up because of some technicalities and bottlenecks. Here we get about a speed up of 20, but it's still really good given. I can bet that I've not seen any other method that can do this other than this. So now I've taken the same problem and I've increased the oxidizer by 100%. So the flow topology completely changes. And I'm using the same adapt to reduce order model in this problem. And more or less it still works, although the movie's out of sync. But the other thing I wanted to mention is this number. I've gone from 500,000 to a dimension of 5. That's it. Okay. But because I'm adapting the solution manifold, it's able to handle it.
What does that mean exactly? Dimension of 5.
Yeah. So let me tell you that technically speaking, if your basis at every time step was the entire solution, then you only need a basis of size dimension 1.
Yeah.
Right? So take the flow field snapshot, right? At that given time. And you make that the basis.
Yeah.
Then you only need that. You only need one basis.
Yeah.
Right? So that's the ideal case. You only need one base, but of course you can't find that. So normally, even for the more complex problems, we don't need to go to beyond 50. But the gold standard is that 1. If you had this perfect way of nudging the basis, it would basically find the exact solution at every time, and you only need one basis. That's what it means.
So you have a dimension of sort of 5 global mode, shape functions, whatever.
Correct.
Represent the entire.
And that's changing. That's changing every time it's changing.
Yeah.
It's because it's changing is why it's possible. Otherwise, it's obviously impossible. Yeah.
Could you go again through the optimization for the sample points?
Okay, so
That one.
yeah, so this is actually a very simple approach. So we have we can reconstruct full field solution, right? And then we already have a basis from the previous time step. S is your sample point selector. I'm trying to find those sample points which reduce interpolation error between the full field and the reconstructed field. So this whole thing here is just like I showed you in that first slide, right? So this whole thing takes samples from a few locations and reconstructs the entire field. And I want to find that S which minimizes this error in the L2 norm.
And what is F again? F is the
F
full field
is-
solution, but not from.
Not from the full order solver. It is still your reduced order projection. So F is, just think of F as a flow field snapshot at the current time that your ROM is predicting. And this is the interpolated version of that from a few sample points. So find me the S that is most optimal.
What's the complexity of finding this signal? Like, is that?
You're paying attention where I've said, where for practical and scalable implementations, we actually don't solve that problem. We basically just pick the few points where the residual is maximum.
Okay.
But Ben Perestorfer has somewhat of an efficient algorithm to do that in order K and time or something. But it's not imperative that we solve this exactly because, so this is going to give you some let's say S number of sampling points. We always oversample. We throw some random samples here and there so that we have some kind of a buffer.
Okay.
But ideally, yeah, we would solve this precisely if we're doing everything else correctly. There are a few more caveats there, which I'm glossing over, that you should.
For the heuristic that you're using,
Yeah.
does it scale like order n, or is it still less than that?
The heuristic can be done in much less cost than N.
What is the N here?
N is the big the dimension of the full order model, or number of grid points times number of unknowns at each grid point.
But you're gonna update but the points number you're sampling is only K, so I guess you want, how many of those fractionally would you update? Is it like 10% or?
In this case, 0.5%.
No, 0.5% is the sample,
Yeah,
but in your sampling point update, right, of that 0.5%, of the points you sample, in each update, like how many are you actually updating? Like, is it,
0.5%. We'll update all of them.
or you'll update all points at every time step?
Yeah. It's only 0.5%, so it's, so that, and there's another bottleneck that's even more serious than that. So, yeah, about 0.51% is what we do. So that sets the best efficiency you can get out of this at 200x, but we actually get only 20x because of one other bottleneck, yeah.
Well, but then that's a lot, right? Because if you're, I thought you would change actually very small fraction of the samples.
No,
If you're, if you're
okay,
changing all the sample.
one thing, we don't, so the basis gets adapted every time step. The sample
Yeah,
points
basis
get
can get
adapted,
Yeah, basis can get adapted every
the
time.
sample points get adapted every ZS, about 25,
But you sample everything, you change everything,
all of the 0.5%.
all of the point.
So you're zooming, that's the place where we need more work in robustification and acceleration, right? So that's what we are kind of working on.
We're at 4:45, 15 minutes.
Yeah, that's
But
fine.
you've been asking a lot of questions, so.
No, it's good, it's a good discussion. Of course, this creates nightmares for parallelization and load balancing because points are moving all over. But I had a very good student who spent a lot of his time doing it, so at least for 2D, he's able to do that. All right, so now the more exciting part, tractability, right? We cannot even run a full order model of the full thing. So how can you build a reduced order model under these circumstances? So this is what we want to do. So can we like do an engine with different number of injectors, different combustion chamber sizes, etc. Okay. So the idea here is we will train a reduced order model for one injector and we'll train it with some perturbations. And then we'll stitch them together to build a combustor. And the information exchange between these two reduced order models happens via a simple flux exchange. Okay. That's the idea. So does it work? We've tried this. We developed this reduced order model using, for this one injector, using some ROM training. And then we stitch them together. I come from compressible CFD, so whenever I see an interface, I get projected solutions on both sides and I apply a simple CFD flux, rho flux in this case. And here is how it works. So here we've taken this single injector type ROM and put 3 of those ROMs together to create this ROM network, as I call it. And this is this unseen full order model solution. And here I'm showing, think of this as some glorified Fourier spectrum, right? This is like the DMD spectrum for pressure and temperature. And it's kind of getting much of the important dynamics. When I stitch 5 of these injectors together, again, I get more or less visually the same kind of dynamics. And when I go to 7, it is still performing well with this beautiful spike here, which it's also picking up. When we go to 7, there is a transverse instability that the reduced order model is also picking up, right? So this is truly emergent dynamics because the training was still on that one injector. Okay. But all of this works because the adaptive basis is good enough that it is kind of more or less giving the right conditions for the ROM to work. Of course, for the highest frequencies, it's not great, and even here, of course, there is some differences, but it's not perfect. There's room to improve. So quickly, I'm coming to the end. Your 3 things to take home is 1, when you have very complex physics or even simple physics, no matter whether you use linear, nonlinear basis, whatever kind of basis you use, it becomes inadequate. That's one thing. And the second thing is to even keep this, I did not spend much time on stability, but again, as I said, we spent a couple of years coming up with methods to keep it stable. And the second thing is whenever you have these kind of complex physics, especially chaotic and aperiodic physics. So this is just a two-dimensional shear layer, okay? So it's just a very simple data set that looks like this. And you compute the singular value spectra for some amount of time, you get this kind of decay. So if I want like 99.9% of energy, I just need like 20 moles. But I use more data, then it's picking up more detail, but it never converges, right? So this is not a problem of the SVD, it is a problem of this is because a static basis is very inadequate, okay? So the adaptive basis is what helps you get there. So yeah, the adaptive basis works, can work in a network. So again, what did we do here? The three parts of the talk. The first part, which I actually spread through all the parts, but the first part was by transforming to a secondary set of variables, scaling, dual time stepping, scaling, and then applying least squares, you can make ROMs stable and well conditioned. The second part was, anytime you have these kind of, you don't even have to go to chaos. Anytime you have this transported convecting features, you need a static basis is not going to be good enough, no matter how fancy it sounds. So we went to the adaptive basis idea, and then stitching together reduced order models gives you the full network. And this is, I would call this major. This took about 8 years and about 15 of us to get to this point. But these things still break, and like you were maybe zooming in on that sampling point selection, I think is one of the single biggest issues, which we are very ad hoc now. There are some methods we're working on, and we also have to do some work in points where we are not sampling. That chokes the solution, right? So making the adaptive ROM more efficient is the main issue. And right now, for the kind of methods that we use, you can get a maximum of 10 to 20 speed up, but because we're intrusive, this takes a lot of time to develop properly, many years. So my student Amir is, at least part of his time is thinking about some non-intrusive ways of doing this, but there's still a lot to be done. And there are many caveats which I skipped over, those are in the papers, okay? And again, there's a lot going on in the center. We are into our 8th year. They still keep funding us for some reason. I just spoke about these 3 parts. There are a few other things that we've done, and you can read about those in that website. All right, I'll stop here and take more questions. Yeah, thank you for a lively discussion.
Any other questions?
Oh, that's cool.
Yeah.
Very nice. I understand better so much better
Oh.
now. So if you do like 10 to 20 times speed up, like another way to get a speed up is close to the grid by a factor of 2 or something like that.
Exactly.
How well do you do compared to?
Exactly. So that's a good question. So I think in some cases, reducing the grid by a factor of 2, which can give you technically, you can also use a 16, yeah. I would not say that it gives, think about it this way, right? So I'm going from here to here with almost nothing that's noticeable, right? And then I can run, technically speaking, I can run one time step of the full solver. And then I would not even see those differences. If I run it on a coarsened mesh, I would certainly lose some of the peaks. But does it actually buy me everything I want? I don't know. It's a good thing. But I think the right answer is maybe a combination of both. Right now, we are trying to apply these techniques in the context of AMR, where that issue comes up directly, right? So do you need to
What's AMR?
adaptive mesh refinement? Yeah, so here we are changing the basis, but you can also change the mesh. What is the most efficient way of doing it? I feel for local structures, AMR can help. For more global things, these methods can help. But yes, I would not claim that this is objectively the best thing to do. But I do strongly believe that some things, like, I think this has an advantage in some particular situations, but yes, if you change the baseline, maybe a factor of 20, we'll run into that issue. Are we really doing better in this global efficiency metric? But if we can break through some of the expense in the sampling, which chokes us to 20, and then we get to 100, then maybe we are much more competitive. But I think the true thing would be a combination of both.
Towards the end of the presentation, you had some examples where you cannot even run the high fidelity model. In that case,
Yeah.
do you have any thoughts on how could you use the adaptive manifold ideas in those cases?
Yeah, that's what I showed here, right? So here, I'm just I'm just training a ROM for one injector, and then I'm replicating them, and they talk to each other and the interfaces. So component ROMs is what we do. Component release elements.
So sorry, you say that the component ROMs, what are they? Are they going to give you the high fidelity simulation?
Yep, that's what I showed you here, right? So here, you have 7 of these. So this is the high fidelity simulation, and this is 7 of those ROMs that are put together.
Yeah,
But this is just for reference. This was not used to train this.
okay.
This is just to validate it. That was not used to train it. So anyway, there's still like the many bottlenecks, and we're trying to address some of them. But yeah, this is I would say that in the field of reduced order models, this is maybe a big advance. But is this the best thing to do given a compute budget? I cannot claim that just yet. India.
It's not a question.
A more general question about these projection-based ROMs. So,
Yeah.
Is there a concern that the reduced order models will violate principle of abelian invariance, or can you build them such that that's not really a problem?
We're still effectively using the same equations as the full order models. So in a sense, that's not a problem. But in practice, because of our sampling, we can violate some conservation properties. But there is a way to still enforce conservation in local domains. But that requires additional cost. Yeah. But yeah, this is not a data-driven ROM, in which case all of those would be big concerns. Yeah.
I guess one question I have is with kind of your full system simulation, like a large engine that's kind of inaccessible by full order model. What are the outputs that you'd be looking for a simulation like that, and then how well do you perform on like those meaningful outputs?
Yeah. There's another paper where we look. So what? In this case, this was an Air Force project, right? What they care about the most is they have a simulation that's running, and then they perturb it. And they want to see how fast the perturbations grow. These are not linear perturbations, these are non-linear, and the reason is combustion instability in rocket engines. You can have these very powerful people. And if you go to YouTube and even say rocket engines, they'll have things blowing up, right? So what they want to know is, what is the growth rate of the instability? It's not linear, it's non-linear, but there is a growth rate. And what is the amplitude at which it saturates? So thing is, every instability grows. For them, unstable means the amplitude reaching some level. So that's their main quantity of interest. And because this problem is so coupled, all of these small scale things matter. Okay, because you don't see it here, right? Sometimes if this instability is strong enough, it'll basically shut the flame. Okay, so it's not something you can just put on a very simple surrogate model for the QIs. At least that's how we sell it, I'm sure. Right? But I think the thing is the small scale things matter. So that's one justification for using these. But I'm sure in an engineering design setting, a surrogate model might get people much further than a reduced surrogate. Yeah. There's one more hand that was up.
Yeah.
Two more, yeah.
Thank you. I think when you're talking about adaptive basis, and you also mentioned stability, I'm wondering, it's a very basic question. So what is the definition of the stability, right?
Stability,
Linear
okay.
stability, or is some?
So we can only guarantee linear stability.
Linear stability.
Yeah, but we can only guarantee linear stability in the CFD solver also. Is right, whatever you learn in your first graduate class is almost the level, the true guarantees you can give. Everything else is prove linear stability and then trust in God. It's the same thing that applies here. Although in some of our work, we guarantee nonlinear stability by using this entropy stable formulation. It's still global, but things can go negative locally. Yeah.
Yeah, I was wondering, do you save the basis as you go along in time, like to reconstruct the whole flow field after the fact, like for example, make the animations, you have to save the basis?
Yeah, we do save the basis, yes. You know, if it was a very simple problem, that cost matters. But here, this is pretty complex and you're running 20 sub-iterations. So saving the basis is not the biggest cost, but yeah, we save it. But only the latest basis is saved, right? Because it gets adapted. You're not saving all of the previous bases.
Okay, so without saving all of those, you can still after the fact go back and like create an animation of the whole flow field. Like in PhD learning, for example, you only need.
No, for the animation, no, the solution is saved.
Okay.
That's it. Yeah. But in reality, unless you have those local bases, you can't, and the local basis coefficients, which you also don't save, you cannot reconstruct it. Okay. This is what you're seeing is just snapshots saved. Yeah. All right, that was good. Yeah.
Wait,
Yeah.
when you go to the expanded model for the full, like for the multiple injectors.
Yeah.
Is there also avenues to like co-train your model with, say, experimental data? You said that in some of these cases, you may not even be able to run the full auto model at time.
Yeah.
And much of the data that you showed was like pressure and temperature, which are scalar quantities, right? So
Yeah.
I'm wondering from the experimental data perspective, will you still need the vector field measurement carefully to help you calibrate those bases?
Vector field, I
Like
mean,
the velocity field, or can you still just train them with pressure and temperature, like scalar quantities that people might measure?
so I mean, you're asking a multi-fidelity question where we can update the model with real data. That's not what we're doing in this context. But we do that in a different context where we know the physics is not accurate. So we introduce some kind of a learning, machine learning model within the base model, and then we solve inverse problem to calibrate the parameters of the neural network. But we don't do that here. Yeah. But there you can deal with any amount of data or any type of data, even as long as it's informative, fine. It can be integral quantities, vectors, it could be point measurements of scalars, doesn't matter. But we don't do that here. The only thing we're doing here is accelerating a given solver, not any other information. All right.
Great. No other question. Let's thank our speaker once again.
Thank you very much.
Thank you for encouraging lively discussion.
Yeah, thank you for all the questions.